This video is brought to you by IXL, used by millions of students worldwide to get ahead in math, English, and more.
Hi there! Today we're going to solve problems using the Central Limit Theorem. Let's say we wanted to measure the mean and the spread of the heights of all the people in New York. We already know that we could collect data from a random sample of the city's population to calculate the sample mean and standard deviation. But what if we kept collecting data from a bunch of different samples of the same population? The sample means are values of a random variable called x bar, and the distribution of the sample means is often called the sampling distribution. The sampling distribution's mean, mu sub x bar, is equal to the population's mean, and the sampling distribution's standard deviation, sigma sub x bar, is equal to the population standard deviation divided by the square root of the sample size, n. But what does the distribution of these sample means look like? That's where the central limit theorem comes into play. It tells us that as the sample size increases, the distribution of sample means approaches a normal distribution even if the population is not normally distributed. So, as long as our sample size is relatively large, greater than 30 is a common rule of thumb, the central limit theorem tells us we can use a normal distribution to approximate the sampling distribution. The z-values for the corresponding standard normal distribution will be x bar minus the mean of the sampling distribution divided by the standard deviation of the sampling distribution. Let's try a few examples. Samples are drawn from a population with mean 172 and standard deviation 34. Each sample has 289 randomly and independently chosen elements. Use the central limit theorem to estimate the probability that a sample mean is between 170 and 172. Firstly, the sample size is 289. That's a large sample size, so we can use the central limit theorem. We need to find the distribution of our random variable x bar and then estimate the probability. The mean of the sampling distribution is equal to the population mean, mu, which is 172. The standard deviation of the sampling distribution, sigma x bar, is equal to the standard deviation of the population divided by the square root of the sample size. That's 34 divided by the square root of 289. The square root of 289 is 17, and 34 divided by 17 equals 2. The central limit theorem tells us we can approximate the distribution of the sample means using a normal distribution with this mean and standard deviation. From here, you may be able to use a calculator to find the answer. But if your calculator only works with the standard normal distribution, or if you're using a table of z-values, we'll need to find the z-values for the normal distribution that correspond to the random variables of x bar equals 170 and x bar equals 172. When the random variable equals 170, the z-value z1 equals 170 minus 172 divided by 2, which is negative 1. When x equals 172, z2 equals 172 minus 172 divided by 2, which is 0. Now we can use a calculator to find the probability that the z-score is between negative 1 and 0, which is approximately 0.341. In other words, there's a 34.1% chance that the mean of the random sample we choose will be between 170 and 172. Let's try another. Samples are drawn from a population with mean 85 and standard deviation 20. Each sample has 325 randomly and independently chosen elements. Use the central limit theorem to estimate the probability that a sample mean is between 83 and 87. Since n equals 325, we can use the central limit theorem. The mean of the sampling distribution equals the population mean of 85. The standard deviation of the sampling distribution equals 20 divided by the square root of 325, which equals 1.109400. Let's now find the z-values that correspond to x. When x equals 83, z1 equals 83 minus 85 divided by 1.109400, which is negative 1.802775. When x equals 87, z2 equals 87 minus 85 divided by 1.109400, which is 1.802775. Now we can plug our z-scores into a calculator to find that the probability the sample mean will be between 83 and 87 is approximately 0.929. Let's try one more. Samples are drawn from a population with mean 98 and standard deviation 25. Each sample has 194 randomly and independently chosen elements. Use the Central Limit Theorem to estimate the probability that a sample mean is greater than 99. Since n equals 194, we can use the Central Limit Theorem. The mean of the sampling distribution will be 98. Sigma x bar equals 25 divided by the square root of 194, which is 1.794895. When x equals 99, z1 equals 99 minus 98 divided by 1.794895, which is 0.557135. Now we need to find the z-value for the upper limit, but there is no upper limit. Let's pick a z-score for the upper limit that would give us a good approximation. Notice that the probability that z is greater than 4 is very small. So the probability of z greater than z1 is approximately the same as the probability that z is between z1 and 4. Great. Using our calculator, we find the probability that z is between 0.557135 and 4, or the probability that a sample mean is greater than 99 is approximately 0.289. Great job solving problems with the Central Limit Theorem today. Keep practicing.
Head over to IXL.com for more practice on this skill and thousands more videos in math and language arts.